Welcome to the course of AI and quantum computing from zero to expert. Hi, I'm Vivin Arana and I'm going to walk you through this course. Now, we have already heard enough about AI. We know what it is, it's artificial intelligence, and there's a lot of different things that you can do with it. But we know very little about quantum computers. And even if we know a little bit about quantum computing, it's still very confusing because it's so new to us. So, first, let's go through a quick introduction. And this introduction, what if I told you that quantum computing is like a magic kitchen where ice cream flavors mix in impossible ways, fries communicate across the universe, and burritos, yes, burritos, hold infinite possibilities. So let's get started and cook up some quantum knowledge using food. So, first, let's talk about classical versus quantum computers. It's like a sandwich versus a burrito. A classic computer works with bits, which are like choosing between two fixed options, just like picking a sandwich with either peanut butter or jelly, but never both at the same time. A quantum computer, on the other hand, uses qubits, which can be both at once, like a burrito filled with rice and beans and cheese all mixed together in one bite. Now, instead of just choosing one option, quantum computing can hold multiple possibilities at once. Hmm, Even though these images are AI generated, they make me hungry every single time I look at them. Let's talk about superposition. It's like an ice cream swirl. If a classical bit is like choosing vanilla or chocolate ice cream, a qubit in superposition is like a swirled vanilla chocolate soft serve. It has both flavors at the same time. Now, in quantum computer, a qubit can be a 0 and 1 at the same time, just like how the ice cream swirl gives you both flavors at once. Next, let's talk about entanglement, which is like a pair of synchronized fries. Imagine you and your friend each order a plate of fries at different restaurants. Even though this image shows in the same restaurant, but if you see the red and the blue, kind of talks about that I am ordering fries at one restaurant and my friend is ordering at a different restaurant. Now, if the fries were entangled, it means that no matter how far apart you are, if you pick up a fry and dip it in the ketchup, your friend's fries will automatically be dipped in ketchup too, without them doing anything. That's how quantum entanglement works. Two qubits are mysteriously connected no matter the distance. Next, let's talk about quantum parallelism, which is like a buffet instead of a single dish. A regular computer is like ordering one dish at a time. You pick a pizza, wait for it, eat it, then order another dish. A quantum computer is like a buffet where you can grab everything at once, be it pizza, be it sushi, be it tacos, pasta, anything, all on your plate at the same time. This allows quantum computers to process many calculations at once, making them much faster for certain tasks. Next, let's talk about quantum measurement, like a mystery box cake. Imagine a cake is inside a mystery box. Now, before opening it, it could be chocolate, vanilla, or strawberry, all at once in a superposition. But the moment you open the box, you instantly find out what flavor it is, and the other possibilities just disappear. This is what happens in quantum computing. When you measure a qubit, it collapses into a definite state, just like when you finally see the cake's flavor. Now, why is all this exciting? Quantum computers aren't just faster computers, they think differently, like a chef who can prepare thousands of recipes at once instead of cooking them one by one. Would you like to try coding a quantum chocolate versus vanilla experiment next? Let's do it. Let's jump into it where we'll be coding a quantum chocolate versus vanilla experiment. Now, again, you don't need to understand all the concepts, but based on what we have learned, if you get some idea of it, that's sufficient. We'll be going in details about all these different concepts in the coming sections, but for this introduction, I just wanted to give you an idea of what we will be looking at and how I'll be teaching this. And after we complete this coding part, I'm going to go over on what all we will be covering in detail in this particular course. So let's get started with coding a quantum chocolate versus vanilla experiment. Here, we will be first installing something called as Qiskit. Again, you don't have to follow along, you just have to look at this video. We will be doing all these steps step by step and introducing each and every library in detail in the following videos in the future section. The second step we'll be doing here is we'll be importing that Qiskit that we installed and set up the experiment. So let's get started. Now Qiskit, which we are going to install, is an open source quantum computing framework developed by IBM that allows us to write quantum programs and run them on simulators or real quantum hardware. Now, it provides tools for building quantum circuits, executing algorithms, and performing quantum error correction. Again, the reason we are installing this is with Qiskit, developers like us can experiment with quantum computing using Python, making it accessible for beginners and researchers alike. So let's go ahead and write code. So for that, what I'm going to do is I would assume here that you have Python installed. If not, we'll be learning about Python and other technologies in future videos. I also added a Python quick up and running video along with this tutorial. So I would suggest you to go through that if you are new to Python. Now, once you have Python installed, and I'm going to go ahead and first step, as I mentioned, let's go ahead and install Qiskit. Now, to install Qiskit, you go to your command prompt or terminal, depending on which machine you have. I have already created a folder here called as AIQC, which is available in the resources section, and you can download all these code files from there. So again, this file that I'm working on right now is I've created a file called as intro to quantumcomputing.py. And inside here, I'm going to go ahead and say pip install Qiskit. That's what you run. Once you run that, you'll probably have Qiskit installed on your machine. Once I have that, I'm going to go ahead and clear here. And next, I'm going to go back to the code file here. And let's go ahead and write the code. So you can just follow along or you can just listen to this, but you don't need to know or implement anything that we're doing because we'll be talking a very high level things here. So it's okay if you don't understand. So I'm going to go ahead and say from Qiskit, import quantum circuit. Now this brings in quantum circuit, a tool for designing a quantum experiment. Think of this as like a blueprint for an experiment in a lab. Next, I'm going to say from Qiskit, import AER. AER is a simulator that mimics a real quantum computer. Now, since real quantum computers are expensive and slow, we use a simulator to test ideas quickly, and that's what is used here. Next, I'm going to say import matplotlib.pyplot as PLT. This is used for making charts and graphs to visualize results. Just like Excel charts help you understand data, this helps us see quantum results. Next, let's go ahead and create a quantum circuit with 1 qubit. So I'm going to say step 1, create a quantum circuit with 1 qubit. And here I'm going to say QC equal to quantum circuit 1, 1. Now what's happening here? We are creating a quantum circuit called QC, short for quantum circuit right here. This is the variable that I've created. The numbers 1, 1 mean it's 1 qubit, like a tiny unit of quantum information, and 1 classical bit for storing those results. Imagine a single coin that can be flipped in a quantum way. That's what I'm doing here. Next, I'm going to say step 2, put the qubit in a superposition like the swirled ice cream that I'm talking about. So I'm going to go here and say qc.h. Here I'm using Hadamard gate, which puts qubit in 50-50 superposition, and we are going to learn more about Hadamard gate later in the future videos. But what we are doing here is we are applying a Hadamard gate, which is H, to qubit 0. This makes the qubit exist in 2 states at once, which are 0 and 1. Now imagine you mix that chocolate and vanilla ice cream together. The qubit hasn't chosen one flavor yet. It's a mix of both. That's what we are doing here. Next, I'm going to say step 3 is measure the qubit, forcing it to choose chocolate or vanilla. So we are forcing it here by saying qc.measure 0, 0. So what's happening here is we measure the qubit, which forces it to decide whether it's 0, which in this case may be chocolate, or 1, which is vanilla. So before measurement, the qubit was in both states. In this particular case, in qc.h0, it was in both states. But once measured, it collapses into 1, either 0 or 1. Example can be, again, another example I can give you is if you shake a coin, it's in a blurry spinning state like superposition. The moment you catch it, it lands on heads or tails, which is measurement here. Next, let's go ahead and simulate the quantum experiment. For this, I'm going to say simulator equal to AER dot get backend AER underscore simulator. So what this line does is it picks a quantum simulator, a fake quantum computer in this particular case, using that AER library we have imported. Next, I'm going to say QC equal to QC.copy. This is copying the circuit. It ensures we don't accidentally modify our original design. Next, I'm going to say QC dot save underscore state vector. This saves the quantum state before actual measurement happens. Then I'm going to go ahead and say job equal to simulator dot run shots equal to 100. Here it tells the computer that run the quantum experiment 100 times. You can increase it 1000 if you want to. It will be a little bit more, it will take more time, but again, depending on how many times you want to run it, you can run saying shots equal to whatever number you want. Then count how many times we get chocolate, which is 0, versus vanilla, which is 1, and assign here. So we'll get those results, and those results I can just say result equal to job dot result. So once I have those results, I can say counts equal to result dot get count. This retrieves the final results like a poll in our case. So next, go ahead and visualize these results. Now to display these results, that's why we have matplotlib. If you've used that before, you probably know what I'm talking about. If not, it's a way to chart the data that we have. So let's go ahead and say flavors equal to, for 0, it's chocolate, for 1, it's vanilla. Then I'm going to say labels equal to, so I'm going to create labels for my mapping for my graph. So I'm going to say flavor.get key comma key for key in counts dot keys. So if I'm getting the data from there, my labels. Next, I'm going to say plot.bar labels comma count dot values comma color brown gold. Now here I am creating a chart. This makes a bar graph because I've said plt.bar showing how often we got each ice cream flavor. So it will display that for us. Next, I'm going to go ahead and add some labels. I'll say X label is flavor, and I'll say Y label equal to count. Again, if you don't understand whatever I'm doing here, I'm going to run this in a moment and you'll see what this shows up to be. So here again, X label, we labeled the graph properly. We said X label is flavor, which is chocolate or vanilla. Y label is count, which is how many times each was chosen. Next, to give the title, I'll say plot.title quantum ice cream machine results. And then to show the, or showing, for to show the chart, I'll say plt.show. This displays the final result for us. So that's our entire application. So I'm going to save this. Now I'm going to go to my command prompt or terminal. Make sure I'm in the right folder. You can just say ls and see that you are in the right folder, and this file is here. And here I can say Python intro to quantum computing. Now depending on what machine you use, you can say Python or Python 3, depending on how you have set up your Python machine. Next, I have results here. If you see, it's pretty much close 50-50 in this particular case. It will be different every time you run it. If I run it again, if you see this time the vanilla is stronger than chocolate, but again, it will display results based on how the machine selects the data out. So here we have created a quantum circuit with 1 qubit. We applied a Hadamard gate to put in a 50-50 superposition, and then we measured the qubit, forcing it to choose between 0 and 1, which is between chocolate and vanilla. And we ran the experiment, as you saw, 100 times to get the results, and then we plotted the results in the bar chart right over here. So I hope it was useful, or just to get an idea of how quantum computing works or how easy it is to implement something in quantum computer. Now again, to learn more on the details of it, you'll have to follow along with the rest of the videos, where we will be learning. First section will be on introduction to AI and quantum computing. Whatever we did just now was just a sample, but we'll be going in much detail in both AI and quantum computing. In section 2, we'll be looking at artificial intelligence deep dive. So after the introduction, I always like to go into a little bit deep dive and learn more about a particular topic. Next, the quantum computing deep dive. So in section 3, we'll be covering quantum computing deep dive. In section 4, we'll be looking at how artificial intelligence and quantum computing work together. So we'll see how we can use both of them together. Section 5, we'll be looking at some advanced applications based on whatever we have learned in the first 4 sections. If you have any questions for me, let me know in the messages, and I'll get back to you.